Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 20, practice section 2, in which we will solve our next problem, number 21, the setup of which is the following. On two distinct points, A and B, they constructed a generating line segment which plays the role of a diameter of a generating semicircle S, shown in white on the left side of your board, and into the planar region trapped between the generating line segment AB and the semicircular arc S, they're inscribed a family of circles S0, S1, S2, and so on as follows. The very first circle, S0, is inscribed into that planar region in such a way that it touches the generating line segment AB in its dead middle, the point T0, which is the center of the corresponding circle S, and that circle S0 touches the circular arc S internally, also in the point that plays the role of the dead middle of the circular arc, which I did not show in order to avoid the clutter, and all the consequent circles S1, S2, S3, and so on Sn are inscribed into the same planar region in such a way that each such circle touches the generating line segment AB at a certain point. Such a circle touches the previous circle externally and the arc of the generating semicircle S internally. Then if we agree that all the circles and semicircles in this problem are named as follows: S, S0, S1, S2, and so on, Sn, the semicircle S, the circle S0, the circle S1, the circle S2, and smaller circles Sn. The centers of these semicircle and the consequent circles is T0, T0, O0, O0, O1, O1, O2, and so on, On. And the radii of the given semicircle and the inscribed family of circles is R, R0, R1, R2, and so on, Rn. Then in this problem, we're given two objectives. First, we need to recover the shape of the length of the radius of the nth inscribed circle, Sn, as a function of the length of the radius of the generating semicircle, R, and the ordinal number of that inscribed circle, n, where n evidently varies over non-negative whole numbers, 0, 1, 2, 3, 4, 5, and so on. The second objective of this problem is the following. If with Tn we designate the ratio of the length of the radius of the generating semicircle R and the length of the radius of the nth inscribed circle Rn, then we are to show that the values the ratio Tn follow the set of numbers shown on the bottom on the left side. For example, T0 is 2, T1 is 4, T2 is 18, 100, 578, 3,364, and so on. Or fundamentally, we need to show that these ratios satisfy the following linear non-homogeneous recurrence relation. Tn is equal to 6 times Tn minus 1 minus Tn minus 2 minus 4. As usual, for best results, we recommend that the moment you comprehend the statement of the problem, you put this video on pause, walk away from the computer, and try to solve this problem correctly and completely on your own. Then come back and compare your ideas to ours. If you manage to solve this problem in a more elegant way or in an alternative way that is better in some sense, we're always curious to hear from you. The comment section is open. Meanwhile, our idea for a solution of this problem that is based on the machinery of inversive geometry is the following. In real time, we kick several ideas around, try and fail a couple of times, but eventually we hone in on the following parameters of inversion. We pick the point A as the center of inversion. The point A is the center of inversion, and technically what that means is that we want to pick the point that defines the generating line segment for the center of inversion in such a way that the family of the inscribed circles goes into the opposite direction towards the other point. If we were to inscribe the circles into the generating semicircle to the left, for example, towards the point A, then for the center of inversion, evidently, we will pick the point B. In other words, the point into which the family of inscribed circles converges is not the center of inversion, but the opposite one. In our case, for demonstration purposes, A is the center of inversion. The power of inversion is positive. We also pick the diameter of the generating semicircle, the distance between the points A and B, or the length of the generating line segment AB, as the radius of inversion. And consequently, by now, we already understand that most of the time we do not really need to draw the circle of inversion. Here I highlighted it in the dashed line. See, this is our traditional circle of inversion. AB is the radius, A is the center, the power of inversion is positive. And now we'll roll through the tidal wave of which objects are taken into which other objects under the chosen inversion. In this case, we see that if we extend the straight line AB, that straight line will be taken into itself, because that straight line passes precisely through the center of inversion. Then we will see that technically it's a semicircle. That semicircle will be taken into the array that is originating at the point B and is going in this direction. This semicircle will be straightened out into a ray, but if we were to complete the generating semicircle S into a full or a complete circle, then that circle will be taken into a straight line that we know, according to the appropriate theorem, will be tangent to the circle of inversion. See, precisely because that circle passes through the center of inversion. And what can we also say about the interaction between the straight line S prime and the straight line AB? Well, we know that under inversion of the real plane with respect to a circle under any power, positive or negative, the tangency points are preserved and the magnitudes of the corresponding angles are preserved. The straight line AB is orthogonal to the complete circle S. Consequently, that means that under the chosen inversion, the images of these two objects must be orthogonal as well. Since the straight line AB is taken back into itself and the complete circle S is taken into a straight line S prime, it follows that the straight line S prime must be orthogonal or perpendicular to the straight line AB extended, and that straight line S prime will pass through the point B, and the fact that this straight line S prime is perpendicular to the straight line AB extended is depicted with this symbol over here, which is how we show right angles in geometry. Once we understand that, it also clear to us now that the family of the inscribed circles Sn will be taken into a family of circles, genuine circles, S prime n. Why is that? Because none of the inscribed circles S0, S1, S2, and so on passes through the center of inversion. We already now know that according to the corresponding theorems, such circles under the chosen inversion will be taken into the genuine circles. But again, precisely because the tangency points under any inversion are preserved, that means that, for example, the circle S0 will be taken into the circle S prime 0 in such a way that if the original circle S0 touches the straight line AB extended, and that straight line is taken into itself, it means that the image of the circle S0, the circle S prime 0, will also touch the straight line AB extended. And because the circle S0 touches the arc of the generating semicircle S, the image of that circle S0 or S prime 0 must touch the image of the semicircular arc S, which is the straight line S prime, and that means that our image circle S prime 0 will touch that straight line S prime at certain point, let's say over here. Consequently, all the remaining circles will behave also in an expected way due to the conservation of or preservation of tangency points. For example, the circle S prime 1, which is inscribed into our generating semicircle, will be taken into a circle S prime 1 shown over here, and that circle will touch the image of its larger neighbor S0 or S prime 0 over here at this point right here, and it will also touch the straight line AB extended. It will touch the image of the circular arc S or the straight line S prime somewhere over here, and it will touch the next circle, which will be the image of the next original circle, and so on. And the question now is, why did we execute this maneuver? Well, technically, what we're doing right now is we're applying the transform and conquer problem solving approach. If you're new to this channel or you joined us later and you missed this episode, we explain in great detail how the transform and conquer problem solving approach works in season 1, episodes 3, 4, 5, 6, 7. If you want, you can search this channel directly or open in your browser in a separate tab the link to the free PDF file that is the season 1 guide. I indexed all the episodes for each season, including season 1, in such a season guide file in all these files, and you can search for these episodes, click on them, open them, and study how this problem solving approach works. But fundamentally, the reason why we executed this maneuver and employed this particular inversion is the following. By transforming a problem, we're putting that problem into the context that is much more tractable for us, and the context in which we gain a tactical or a competitive advantage. Look, the original problem is curved. Let's say, parabolically speaking, it's curved and it's difficult to solve. But the transform problem is uncurved in a way. It is, in some sense, a rectilinear situation where we have a family of circles S prime 0, S prime 1, and so on, inscribed not into a complicated shape, such as a semicircle, but into a straightforward shape. If we were to bound the circle S0 into a square, then technically we would have a family of circles inscribed into a square as shown, and dealing with circles that are inscribed into a right angle specifically is much more pleasant than dealing with circles that are inscribed into a complicated planar region that is bound by a circular arc. And without even going into many details of what is about to happen, precisely because we're dealing with a square, we can already make a fearless prediction that the square root of 2 will make its star appearance in the upcoming calculations. And another aspect that I wanted to highlight is the following. As a technical person, you're always skeptical about your work. You want to double check your work. One of the best ways to check the correctness of your geometric constructions is to animate your construction, wiggle it, let it breathe, let it move around. If all the objects under this dynamic situation behave reasonably, behave well as expected, then chances are high that you did your construction correctly. It's not a guarantee, but the chances are high. As such, I've put a sample GeoGebra based animation for you of this situation over here to show how this reflection business works. And in the animation that you're about to see, I fixed the point A, but I animated the point B. I let that point roam a portion of the plane in a straight line. It doesn't really matter. It doesn't have to be anything complicated, but you will see in a few seconds that the point B will breathe, will move around a little bit. It will orbit a certain line segment. And as that point moves, the whole contraption, all the objects, the original ones and the reflected one, will behave in a certain way. Once we hone in on a successful inversion, we flesh out our angle of attack as follows. Sometimes it is quite helpful to inquire how this or that construction was carried out in the printed material. The free PDF file, which captures the corresponding chapter of my free book, Inversive Geometry for All, on which this practical practice session is based. You will see a mathematically precise construction, and the question is how that construction was carried out. Actually, that was the question that I was facing when I was writing the book and the corresponding chapter, and it turns out that, among other things, that is very helpful in this case is the geometric transformation of homothety, or uniform expansion or contraction of the corresponding plane. As such, we exercise the tactical advantage afforded to us by the transform and conquer problem solving approach by solving an easier, in some sense, or much more tractable inverted problem, because we have a family of circles inscribed into a square essentially. And we do that by constructing the function that will capture the length of the radius r prime n of the nth inverted inscribed circle as a function of the radius of the generating semicircle S and the ordinal number of that circle n. And we will do that by observing again that the family of the circles, reflected circles S prime n, is homothetically similar if we carry out the corresponding homothety of the parent plane with respect to the point B. That means that, for example, if we uniformly expand the parent plane with respect to the point B by the certain ratio, then, for example, the smallest circle over here, hopefully you can see this little bit, circle, let's say we'll call it S prime 2, will be taken into the circle S prime 1. The circle S prime 1 will be taken into the larger circle S prime 0, and all the previous circles will behave in the same way. And conversely, if we uniformly contract the parent plane with respect to the center B, then by the corresponding transformation, the larger circle S prime 0 will be taken into the circle S prime 1. The circle S prime 1 will be taken into the circle S prime 2, S prime 2 into S prime 3, and so on. So by exercising the fact that all the circles from the family of reflected or inverted circles S prime n are homothetically similar, when the homothety of the plane is carried out with respect to the point B, we construct a function of the radius of the generating semicircle S and the ordinal position or ordinal number of that circle for the length of the radius r prime n. Then we will capitalize on another fact. We'll construct another function that connects the radius of the nth inscribed original circle to the length of the radius of the reflected circle, and reflected circle r prime, and this will be another function f. Here we will construct this function based on this fact over here. There will be another homothency at play over here, but this homothency will be based at what center? Not at the point B, but at the point A. Look at this. Here we will use the fact that now we have two families of circles, the family of the original inscribed circles and the family of reflected or inverted circles. And pairwise, these circles are now homothetically similar if the homothency is carried out with respect to the point A. In other words, we have the circle Sn homothetically similar to the circle S prime n when the homothency is carried out with the center at the point A, which means that, for example, the following: a uniform expansion of the parent plane with respect to the point A will take the circle S0 into the circle S prime 0, and conversely, the uniform contraction of the plane will take the circle S prime 0 back into the circle S0. Likewise, again, this is drawing that I did over here on board is by hand. I'm limited by the real estate. If you look at the printed material, the construction over there is carried out with mathematical precision. Everything makes sense, but you will see that, for example, then homothency is centered at the point A. The expansion or contraction will do the same thing for the circles Sn, S1, and S prime 1. The expansion or the contraction will take the circle S1 into the circle S prime 1, S2 into the circle S prime 2, and so on. And once we have captured this function, then the solution will become evident and obvious. We simply take our function theta, this guy, inject it into this function over here, replacing this material with just this material, and voila, we have our function that we are required, this guy right here, that we are required to construct. Observe that these things happen in both elementary and non-elementary mathematics at all times. If originally we managed to pick a right direction to go in, then things fall into place nicely and every step of the way works out in our favor. And conversely, if originally we did not manage to pick a right direction, then every step is a nasty and a grueling fight. In this particular case, because we managed to pick a successful inversion after several try and fail attempts, things work out nicely, and the unfolding solution cannot be qualified in any other way than basically a child's play. Look at this. The length of the radius of the largest reflected circle r prime 0, which is the distance from the center of that circle O prime 0 to the point T0, or the distance from the point T prime 0 to B, the distance BT prime 0, this distance right here, can be represented as a composite quantity, as the difference between the distance from the point A to the point T prime 0, this distance right here, and the distance AB, which is the diameter of the generating semicircle S, and this is what we captured symbolically. The length of the radius r prime 0 is the distance between the points B and T prime 0, among other things, which can be represented as the difference between the distance between the points A and T prime 0 and A and B. A and B is the generating line segment, which plays the role of the diameter. It is equal to 2r. And why did we hone in on this particular representation? Well, because the points T0, remember T0 and T prime 0 are what? They are the inversive images of each other under the chosen inversion, you see? The point TO by this inversion is taken out of the circle of inversion C outside, and conversely the point T prime 0 is taken inside. Consequently, that means that according to our condition 3, definition 1, the product of these distances is locked into the following relationship. It is equal to the square of the radius of inversion. The radius of inversion is 2r. The square of 2r is 4r squared, from where it follows that for the distance at prime 0, we have 4r squared in the numerator, the distance at0 in the denominator. And what is the distance between the points a and t0? Precisely, that is the radius of the generating semicircle. As 4r squared divided by r is 4r. Consequently, that distance at prime 0 is 4 copies of the radius of the generating semicircle. And putting this result back into this expression, we obtain r prime 0 is nothing more and nothing less than 4r minus 2r, which is 2r. And this is our first result that we will use in a second. Now we use the fact that the entire family of the reflected circles S prime n is homothetically similar in the following fashion. Any two immediately adjacent circles, or any two circles that touch in that family, are precisely the homothetical images of each other under the homothety of the parent plane with respect to the point B. In other words, as I explained before, if the parent plane is uniformly expanded by the corresponding coefficient of homothety, then the, for example, circle S prime 1 will be taken into the circle S prime 0, and conversely, if the entire parent plane is uniformly contracted with respect to the point B by the corresponding amount, the coefficient of homothety that we will call a rho, a constant real number, then the larger circle, reflected circle S prime 0, will be taken into the smaller reflected circle S prime 1. And one computationally convenient magnitude that we can use in order to capture the coefficient of homothety of the plane that is centered at the point B is the ratio of the length of the radius of the reflected circle 1, r prime 1, to the length of the radius of the previous reflected circle r prime 0. The way we wrote it, evidently the logically next circle is smaller than the previous one. That means that this particular ratio, which we name rho, is a constant real number such that it will be strictly less than 1 and evidently strictly larger than 0. This particular coefficient reflects the uniform contraction of the plane, but it doesn't really matter. If we take the reciprocal 1 divided by rho, and that number is strictly larger than 0, then we will get the expansion, so it doesn't really matter. But from this relation, it follows that the length of the radius of the first reflected circle r prime 1 is expressed through or via the length of the original, or zeroth, if you will, reflected circle r prime 0 as follows. It is the product of the coefficient of homothety rho and the length of this radius r prime 0. But the way this homothety, the geometric transformation of homothety works, is that the meaning of the word uniform in the definition of this transformation is the following. As, for example, let's say we uniformly contract or make everything smaller, contract the parent plane, and we take the circle S prime 0 into circle S prime 1. At the same time, that means that the circle S prime 1 will be taken into the circle S prime 2. And this is captured over here. It means that the ratio of the lengths of the radii of the second reflected circle to the length of the radius of the first reflected circle is the same number, rho. You see, this is This is the uniformity of this geometric transformation by the ratio by which we contract the parent plane that takes the circle S prime 0 into S prime 1. That same ratio will take, or that same, the contraction of the parent plane by the same ratio will take the circle S1 into circle S2, make it smaller by the same amount, rho, and from here it follows that for the length of the radius of the second reflected circle r prime 2, we have r prime 1 times rho, but r prime 1 is taken from here, so we take this number and put this expression over here, and what do we have? We have r prime 0 times rho squared. Again, because the transformation of homothency is uniform, it means that as the circle S prime 0 is taken into the circle S prime 1, S prime 1 is into S prime 2, S prime 2 into S prime 3. It means that the length of the radii of the third reflected circle and the second reflected circle in the corresponding ratio will amount to the same constant real number, rho. And from here it follows that r prime 3 is equal to r prime 2 times rho. Again, for the length of r prime 2, we take this right here expression from here and put it back, and what do we have? R prime 0 times rho raised to the third power, and so on. If we keep rolling, then for the length of the radii of the nth and n minus first reflected circle will have the same ratio, rho. From here it follows that r prime n by length is equal to r prime n minus 1 times rho. And if we go through all these substitutions and eventually put this substitution into r prime n minus 1, we will have our product r prime 0 times rho raised to the nth power. You see, nth, the length of the nth radius of the nth reflected circle is r prime 0 times rho to the n. This is captured over here for all values of n that vary over 1, 2, 3, 4, 5, and so on. But we already know that r prime 0 is what? Remember, we deduced this relation a few seconds ago. So now we can express the length of the radius of the nth reflected circle via the radius of the generating semicircle S. And if we can somehow recover the name, the actual name of this constant real number rho, then we will construct our, remember we originally said that we want to construct a function theta that connects the radius of the generating semicircle and the ordinal position or ordinal number of that circle. If we uncover, unmask, or reveal the name of this real number, then voila, we will have our function theta of r and n. And the next step, where the synthetic geometry meets the corresponding algebra, or in some very light sense analytic geometry, is very straightforward and amounts to the following. Look at this. So far we proved that r prime 0 is twice the radius of the generating semicircle. We proved that this relation over here holds, and now we want to unmask the name of the real number rho, which is the coefficient of homothency with respect to which, when this homothency is centered at the point B, all the circles in the family of the reflected circle, of the reflected family, one to immediately the next one of the previous one, are homothetically similar. So we do that by this observation over here. We loiter around the line segment BO prime 0, this point right here, which is the center of the largest reflected circle S prime 0. This distance is, again, can be computed in two distinct ways. So in some sense we hijack or borrow the idea of double counting popular in combinatorial analysis, but we also can use double counting, for example, to evaluate certain finite sums, as we did this on this channel already. So on the one hand, that distance over here is the diagonal of the corresponding square, and as the diagonal, that magnitude is equal to what? Well, the side scaled by multiplied by the square root of 2. You see, this is when our fearless prediction a few segments ago materializes or realizes itself. The square root of 2 found its way into the woodworks. So that is on the one hand. On the other hand, again, this length, this distance, is the composite quantity which is put together from the distance from the point B to the center of the circle in reflected circle S prime 1, B O prime 1, this distance right here, plus the distance from the center of the reflected circle 1 to the distance of the reflected circle 0, this distance, O prime 1, O prime 0. But this distance again is dialed in from two distances right here. The distance R prime 0, the radius of the reflected circle S prime 0, and the distance of the radius of the circle S prime 1, the reflected circle S prime 1. So this is captured over here. This distance BO prime 1, this distance is again the a diagonal of what? Of the corresponding smaller circle and so on. So that distance is the side of the square, or R prime 1 times the square root of 2, R prime 1 times the square root of 2, plus the distance between the centers of two circles that touch each other externally, which is the case in our reflected family of circles. Again, we linearized in some sense, or uncurved, if you will, our difficult to solve original problem. This is where we reap the benefits of all these beautiful childish manipulations, R prime 1 plus R prime 0. So now we omit this material, we take the left side, the right side, and we join them. And this is what we get. R prime 0 times the square root of 2 is R prime 1 times square root of 2 plus R prime 1 plus R prime 2. Now we take this relation and uniformly divide it by R prime 0, shown over here in the middle. Evidently, the trivial arithmetic, this ratios is precisely what we call our real number row, and everywhere else R prime 0 and R prime 0 cancel out. We obtain this particular relation. Square root of 2 is equal to row scaled by square root of 2 plus row by itself plus 1. From here, trivially, we factor out row, square root of 1, square root of 2 minus 1 in the numerator, square root of 2 plus 1 in the denominator. This is our intermediate result. We multiply both sides of this ratio by what? By the conjugate image of the denominator, which is square root of minus 1. In the denominator, we get a squared minus b squared, difference of squares. 2 minus 1 is 1. And in the numerator, we get square root of 2 minus 1 squared. 2 plus 1 is 3. 3 minus 2 square roots of 2. Boom. This is how we unmask the name of the real number row, and it can be readily verified that this number is less than 1 strictly and greater than 0 strictly. Consequently, if we slug in row into our original relation that we developed in the previous segment, this relation is shown over here. R prime n is 2 times r times 3 minus 2 square roots of 2 raised to the power of n, and varies over all non-negative whole numbers 0, 1, 2, 3, 4, 5, 6, 7, and this is our function theta of r and n. Wonderful. We can now move one step closer to answering the first question in this problem and constructing the function theta phi of r and n for the length of the radius Rn of the nth inscribed circle in this case. And we do that by constructing the function that binds together the length of the radius of the nth inscribed circle and the length of the radius of the nth reflected circle r prime n. Here we do that based on the idea, on the observation that the family of original and reflected circle pairwise, circle by circle, original circle, reflected circle, original circle, reflected circle, are homothetically similar if the homothenity of the parent plane is carried out with respect to the point A. One way to capture the coefficient of this, let's say sub index k, means that the k designates the coefficient of this homothenity at the center A, is shown over here. We basically take any distance between the center of inversion and the center of inversion and the distance from the center of inversion to the inversive image of that point, for example, at0 and at prime 0, at1 and at prime 1, and so on. This will hold for any n, and we construct that coefficient as follows: the ratio of the distances from the center of inversion to the point Tn and T prime. And again, the meaning of this point T is understand. This is the point where all the inscribed circles, and for that matter, all the images of the inscribed circles, touch the straight line AB extended. And this is one way to capture the coefficient of this homothenity with respect to which, centered at A, the circles, the original circles, and the reflected circles are the homothetical images of, for example, the circle S0 by the uniform expansion of the parent plane centered at the point A will be zoomed out into the circle S prime 0, and conversely, the circle S prime 0 will be zoomed in, contracted into the circle S0 if we take this another constant real number as a coefficient of homothenity. Why did we pick these points? Well, we picked these points because we know that according to the condition, what is it, 3, definition 1, this is the workhorse relation that captures the algebra of inversive geometry, the product of the distances from the center of inversion to the inversive images, to the inversive points, is equal to the square of the radius of inversion. The radius of inversion is 2r. We captured it over here, and I still kept it. 2r. 2r squared is 4r squared. From this relation, we have for the distance between the points A and Tn, this relation over here, the ratio of 4r squared in the numerator and the distance from the point A to the point T prime n in the denominator. Consequently, if we put the image of the distance A, Tn, from here back into here, we will obtain the following ratio: 4r squared over the square. You see, this is where we again win in some sense, the square of the distance from the point A to T prime n, the point T somewhere over here outside of the circle of inversion. See, and the coefficient of homothenity, again, because the homothenity is a transformation that acts on all the points of the parent plane uniformly. That means that all the homothetically similar distances will be changed by the same amount, k. So the ratio of our radii, Rn to R prime n, also will be k, because precisely of the homothenity centered at A and the coefficient k. This is how we capture the fact that the homothenity at the center A will take all the original circles into their reflected images pairwise, not in some haphazard fashion, but pairwise. S0 into S prime 0, S1 into S prime 1, S2 into S prime 2, and so on. And now we have this relation over here. If we express Rn in terms of R prime n over k and use the image of k shown over here, this is the relation, that the intermediate relation that we will obtain. And remember, all the material packed into the length of the nth reflected circle, R prime n, is already known to us. We deduced it a few seconds ago. It is given by this expression over here, 2 times r times 3 minus 2 times square root of 2 raised to the power of n. This material is known to us. So now all we have to do is concentrate, express this square of this distance in terms of the locally available material. And in order to do that, we swing back temporarily to the fact that the family of the reflected circles S prime n is homothetically similar in the homothency of the parent plane that is centered at the point B. And just in the same way we chase down, remember how we did in a way, inductive reasoning for the length of the radius of the nth reflected circle r prime n to r prime o, we show that is equal to rho raised to the power of n. The same way we can do the same chase for the linear distances from the point B to the nth image t prime n of the point corresponding point Tn, and with respect to the distance from the point B to this point right here, Bt prime 0. In other words, we will say that the initially the distance from the point B to the point T prime 1 divided by the distance from the point B to the point T prime 0 is rho. Then we will do the same thing for the distances Bt prime 2 to Bt prime 1 and so on. We will unzip this into this here expression. It will be the same thing. From here we already have our relation that we showed earlier a few segments ago, and now that's the whole reason that how do we connect our distance from the point A to the nth image of the original tangency point T prime n. Well, again, this distance from the center of inversion to the nth tangency point of the reflected circle and the straight line AB extended can be represented as a composite quantity. The distance AB, always the radius of the circle of inversion, 2r, plus the itsy bitsy piece that is left over here. This is the distance from the point B to T prime n, these two distances. 2r, and this distance Bt prime n is taken from here. You see, similar to this relationship, it will be Bt prime n, it will be Bt prime o times rho of n, and Bt prime 0 is what? Is r prime 0, and r prime 0 we already proved it is 2r, where r is the radius of the generating semicircle. 2r plus 2r times rho raised to the power of n. This is all middle school arithmetic, nothing complicated over here. So now we have our distance from the point A to the nth reflected point T prime n as 2r times 1 plus rho raised to the power of n. We unmask this value of this real number rho, the homothency of the reflected circles. We know what's going on. Now we go back to the formula that we saw a few seconds ago, and simply into the denominator of that ratio we slug in the square of this number. So what do we get? 4r squared in the numerator, 4r squared plus the factor of 1 plus rho raised to the power of n squared. This is shown over here. 4r squared times 1 plus rho raised to the power of n squared. 4r squared cancel out. So k is basically 1 over this monstrosity over here, and the game is over. We take our radius of the nth inscribed circle as n. And now remember, we said that this pairwise, the original and the homothetically and inverse image of that original circle are homothetical when the homothency is carried out of the parent plane with respect to the point A. This is captured over here, and now we simply take this k and put it over here. And what do we have? For r prime n, we take r prime o, which is what? 2r times rho raised to the power of n, 2r times rho raised to the power of n times k, which is what? 1 over 1 plus rho raised to the power of n squared. That's it. Game over. Now we simply spell out the square. 1 plus 2 times rho raised to the power of n plus rho raised to the power 2n. And now we divide the numerator and the denominator by the numerator, rho to the power of n. So what do we get over here? Here we will have only one copy of rho raised to the power of n. Here we'll just have 2, and here 1, the reciprocal of this image. So this is our function that we were trying to recover. This is our function phi r of r and n for the length of the radius of the nth inscribed circle. Game over. We have this function right here, 2 times r times 1 over rho raised to the power of n plus 2 plus rho raised to the power of negative n. Rho is this ratio right here, or 3 minus 2 times square root of 2. A random mathematical butterfly is a happy thought that may come to you as you work in one layer of mathematics and you recognize something that you have seen in a different layer of mathematics, and sometimes it so happens that this thought or this butterfly is truly random. That doesn't really mean anything, but sometimes it is actually not that random, and such a butterfly is a manifestation of the fact that two seemingly disconnected layers of mathematics are actually connected, and most of the time our feeble minds, my including, are not capable of finding that connection. But once in a while there comes along a person and says, hey, gee, look, these two layers of mathematics are connected precisely because this seemingly random mathematical butterfly that connects the two is not really that random, but it is a hefty mathematical phenomenon that connects the two layers of mathematics. So here, as I was working on this problem, look, we recovered the length of the radius of the nth inscribed circle Sn Rn as a function of the length of the radius of the generating semicircle S and the ordinal number of that inscribed circle n. That function is shown over here. It's a ratio of two numbers, 2r in the numerator and rho raised to the power of n plus 2 plus rho raised to the power of minus n. And we unmask the name of this real number, rho, as a ratio of two numbers shown over here, or its synonym over here. And in integral calculus, you may come, or actually I have come across the following interesting result. It's shown over here. This is the result, so it's easier for you to see. This is the result. The integral from 0 to pi over 2 of x over sine of x as a trigonometric function plus cosine of x, integration over dx. And we will perhaps compute this integral on this channel. We will show a step-by-step deduction of how this result is developed. But look, it comes out to pi times square root of 2 over 8 times the logarithm of precisely our favorite real number rho. Here it's taken as a reciprocal, but it doesn't really matter the way we wrote it over here. It's less than 1. It corresponds to the contraction of the plane. When we take its reciprocal, its expansion of the plane, it doesn't really matter. It's the same thing essentially. So if we render the value of this here definite integral in terms of our real number rho, this is what we get. Again, maybe this is a truly random mathematical butterfly that doesn't really mean anything, or maybe you can uncover a connection between this here geometric problem, the corresponding non-homogeneous linear recurrence relation, and this wonderful little integral. Lastly, we move on to the task number 2 of this problem and show that the ratios Tn satisfy the following non-homogeneous linear recurrence relation shown over here. Non-homogeneous means that we have a free-floating term -4 over here. Without this term, it would have been a homogeneous linear recurrence, and the way we do that is by improvising a little bit. Again, you can see that even though the material that we study over here is elementary, you still have an opportunity to think like a mathematician and improvise and show your technical ingenuity and creativity. And here, this ingenuity and creativity comes down to recalling the middle school algebra theorem, otherwise known as Vieta's theorem or Vieta's formulas, however it is known to you. So here, look, we already in the previous segments, we recovered the shape of the length of the nth inscribed circle as the function of the radius of the generating semicircle, and the ordinal number of that circle is shown over here. It is a small font, but in your records you have it in a nice blown up view. So the point here is because of 2r, we multiply our ratio Tn, which is r divided by Rn by 2 on both sides, and we get 2 times Tn is equal to 2 times r over Rn. And from here it follows what? It follows that 2Tn is equal to, when 2r in the denominator and 2r in the numerator of the multiply by 2 ratio cancel out, and then we have this animal over here. It's a reciprocal, so it jumps into the numerator. It becomes this expression all by itself, and we know that we can replace these guys with 3 minus 2 times square root of 2 raised to the nth power plus 2 plus 3 plus 2 times square root of 2 raised to the nth power. Again, this should be no magic. When we take the number that is shown over here, we take its reciprocal, again, multiply both sides of the resultant ratio by the conjugate. We have 9 minus 8 is 1, and in the numerator we have this no magic. So we know that rho is equal to this number shown over here, then its reciprocal is this. Again, I just explained how it works, why it happens. This is a standard maneuver in complex analysis. In real analysis, when we work with real numbers, conjugates of certain numbers that have a particular structure are quite pleasant. So here in vacuum, in real time, when you stare at these two numbers, you may think, so what? How can we extract actionable mathematics from it? Well, this is where your ingenuity, creativity as a mathematically inclined thinker comes in. And this maneuver shows up in other areas. And we will see it on this channel time and time again. Look at this. How about we sum these two numbers, rho and its reciprocal image? Well, this sum will wipe out the irrational numbers. -2 times square root of 2, +2 times square root of 2. 3 plus 3 is 6. So for the sum of the homotopy coefficient rho and its reciprocal, we have 6, which is a whole number. And for their product, we don't even have to think. Something times its reciprocal, if it's well defined, it's 1. And indeed, 9 minus 4 times 2, 9 minus 8 is 1. Again, these two products come out to what? A squared minus b squared. A is 3, b is 2 times square root of 2. The arithmetic is not even middle school. This is your elementary baby arithmetic. Now we go back to middle school and recall our favorite Vieta's formulas, if you will, or Vieta's theorem, however it is known to you, for a quadratic polynomial ax squared plus bx plus c. When we equate it to 0, its roots, rho 1 plus r2, sum to negative b over 2, and the product of these roots, rho 1 times rho 2, comes out to c over 2. This is the values from the Vieta's formulas. In our case, we already know what these numbers are. A must be 1 because the sum over here is a whole number. 6 divided by 1 is 6. And then b is equal to -6, c is equal to 1. we construct based on this template and these numbers. We animate the template with these numbers, and we have our quadratic equation: x squared minus x plus 1 equal to 0. Bingo. We have our number. And as a side remark, which I will not dive deep into it, but this is the so-called characteristic equation of the homogeneous linear recurrence relation, shown over here without the -4 term. The so-called characteristic equation, which allows us to solve the underlying recurrence relations in the fast and furious manner, which on this channel for the most part we will only do sometimes. I will show how to solve these recurrence relations analytically by hand. It's a long and scenic route, but there is quite a bit of hefty mathematics in there. In any case, this equation over here means what? That our real number rho is such that when it is injected into that equation, it will turn it into identical 0. So rho squared minus 6 rho plus 1 must be 0. And depending on how you want to dance this dance, if you divide this left-hand side of this equality sign by rho squared, you will get this. It doesn't matter. Or we already showed that the reciprocal is the usual suspect over here. It means that it will satisfy the equation when injected over here, and that means what? Rho raised to the power minus 2 minus 6 over rho plus 1 must be identical 0. Remember these two relations. We will need them soon. And now what we do is the following. We go back to our recurrence relation, multiply through by 2, because this is how we remember. This is how we started this whole business. Multiplying by 2 is just computational convenience. There's nothing right now fundamentally interesting to it. Multiply through, carry out all the terms from the right hand side to the left hand side of the equal sign, and represent this difference as follows. Now we check 2 times tn minus 6 times 2 tn minus 1 plus 2 tn minus 2 plus 8. Where did this come from? When we carry this term over the equal sign, it flips with positive sign. Minus, this flips to the sign plus, this side flips to the sign plus. 4 times 2 is 8, 2 to 2 we carried out through this computation trivially. Now we go back and we take these images, all these images for 2tn from this here formula. So we substitute. This is our first term, rho raised to the power of n plus 2 plus rho raised to the power minus n minus 6 times here n minus 1. So we put rho n minus 1, 2, and here rho n minus 1, reciprocal 1 over. Plus 2 of these guys. So we take it from here. So this will be just rho raised to the power n minus 2 plus 2 plus 1 over rho raised to the power n minus 2 plus 8. This is nothing special. Now we count, let's say, the free floating terms. What do we have? Here we have 2. Here we have minus 6 times 2. So 2 minus 12 minus 10 plus 2 minus 8. Minus 8 plus 8 is what? Big fat 0. Free floating terms are gone. And now next we group all the direct powers of rho, or positive powers if you will. Rho raised to the power of n, 6 copies of rho raised to the power of n minus 1, and 1 copy of rho raised to the power n minus 2. Factor this guy out right here. And what do we have here left? Well, from this term we'll have left rho squared minus 6 times rho, 6 times rho plus 1. And next we group all the reciprocals of rho and factor out rho raised to the power of n minus 2, reciprocal of course. From this term we will have left what? 1 over rho squared minus 6. Where is it? Where is this guy? This guy, minus 6 copies of this term. We will have 1 over rho plus 1. This will be this term right here, which is what we factored out. And this is what we have. Now we go back to our observations that we made earlier. Remember this observation and this observation. I will not draw arrows, you understand. From here we come to here. So this is an identical 0. Remember this. This and this, this and this is identical 0. This. Now look at this. This and this is identical 0. So 0 times non-zero number, 0 times non-zero real number. 0 plus 0 is 0. So this comes out to identical 0. And that precisely means that this expression over here is equal to 0. And once we partition this expression back into what's shown over here, divide by 2, cancel, 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 cancel. And this is precisely what it means for us. We just proved that this is really the case. So the question is, how did the person who constructed this problem come up with this? Well, in some sense, admittedly, we need to exercise some powers of perspicacity over here, but it is not entirely impossible to basically reverse engineer this string into this relation over here. So we start with this. We make these observations. They're fairly trivial, nothing beyond middle school. So once we construct these two guys and then we unzip them, of course, we will need to carefully manufacture these numbers. From 0, we need to manufacture 8, 2, minus 12, and 2, admittedly, but in some sense, knowing how the structure of this term looks like, that is not entirely impossible. This is quite feasible. So in reverse order, we come to this. And then once we realize, aha, look at this. This is a nice relation. Well, we package it this particular way. And we give this problem to the students and ask them to solve it. And then once we have this relation over here on the books, we can actually go back and look at the few initial numbers for our ratio Tn. And finally, as a sanity check, we crunch through the formula that we obtained earlier and generate the first several numbers for our ratio Tn shown over here to double check that the people who constructed this problem really gave us a truthful statement. To that matter, we construct the double array number T0, T1, T2, T3, and T4 because this is just simpler to deal with, so we don't have to deal with fractions. So this this relation over here deals with the 0th power. In the 0th power, 3 minus 2 times square root of 2, 3 plus 2 times square root of 2. That is easy to verify. So twice T0 comes out to 4, which implies that T0 is 2, correct. Twice T1 comes out to, once we do all the powers, to 8, which implies that T1 is 4. Now, when we do twice T2, we raise these two numbers over here to the second power. We see that in this case, all the irrationality is erased because these numbers will be cleared of radicals, and the numbers that are not cleared from radicals because of this minus sign will cancel each other out. This 36, this implies that T2 is 18. The same exercise for the third powers. Again, look at this. Third power minus 1 will make sure that the third powers of irrational numbers cancel each other out with positive powers. So the result is 200. This implies that T3 is 100. For T4, again, fourth power even number, enough juice to erase all the irrationality here and cancel out the odd powers of square root of 2. 1156 divided by 2 comes out to 578. That is correct. We can carry out this computation to our heart's content. So these numbers match. The next number will be 3364, and on and on and on. And that means that purely geometrically, look at this. Not only that, in a fairly truthful statement, inversive geometry discovered or generated a non-homogenous linear recurrence relation shown over here. Of course, we know what we have to shoot for, but inversive geometry also managed to solve this here non-homogeneous linear recurrence relation in a purely geometric fashion or by purely geometric means, which means that technically, once we pose this type of questions, we have to specify the initial conditions. T0 is 2, T1 is 4. Then this here non-homogeneous linear recurrence relation is solved over here in the so-called closed form or an alternative expression as a function of n. As a function of n, our coefficients Tn are given by this here formula, which is basically our original result, which I divided through by 2, and this is the result that we obtain. And this concludes this practice session. But on this channel at some point there will be an episode. I recommend that our viewers take a note of that and look for it. I will show how this solution can be developed purely analytically by hand and without this wimpy characteristic equations. What we will do in general is the following: we will multiply everything by x to the power of n, then we will sum the result through by the corresponding coefficients. We will use the initial conditions to inject them into our sums. We will construct an equation for the generating function. Then we will find the shape of the generating function, and then we will decompose it into power series. And in the power series, bam, 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 it will come out precisely that. And this coefficient tells you what? That in the portrait of this generating function, there will be our favorite function 1 minus x. One of these terms comes precisely from this. These two guys are actually quite hairy. Quite a bit of work needs to be done analytically, and this is precisely why it would be beneficial for our viewers to actually see how this result is obtained, not geometrically but purely analytically.